Yeah, okay. So let me share the slide first. Okay, so you can see the slides, right?
Yes, Ranjit, your slides are visible.
Yeah, all right. Okay, so today's talk is based on two of my research work. One I have done with my PhD supervisor, Dr. Anirban Banerjee, and another one with my postdoc supervisor, Dr. Rajesh Khanna. We start with some observations. So we consider matrices with constant row sum. So first one, we take a 2 by 2 case. So we have a matrix A like that, minus 1, 4, 2 and 1. And we take another matrix P like that, 1, 0, 1, 1. So in other words, we can say that P is a matrix whose first column is all one vector and second column is the second standard basis element of R2. Now we then P inverse AP, we do this multiplication. So first of all, you see that matrix P is non-singular and its inverse is minus 1 0 minus 1 1. And after multiplication, we get a block upper triangular matrix like that form, where the leading element here is equals to the constant row sum. For the second example, we take a 3 by 3 case. Here the constant row sum is 4. In that case, we take P to be the matrix whose first column is the all one vector, second column the second standard basis element of R3, and third column third standard basis element of R3. In that case, the matrix P is again non-singular and its inverse is like that 1 0 0 minus 1 1 0 and minus 1 0. And after the multiplication P inverse AP, in that case we are getting a block upper triangular form where the leading coefficient here is 4, which is equals to the constant row sum of the matrix A. Now, from this observation, we try to generalize this fact for n by n case. For that, we take E to be the all one column vector and E prime to be the column vector whose first entry is 1 and all other entries are minus 1. We define the matrix P as P whose first column is all one vector and then E2, E3 up to En, where E2, E3, En are standard basis element of Rn. In that case also, we can prove that the matrix P is actually non-singular and its inverse is the matrix with first column equals to E prime, then E2, E3 up to En. Now, we try to perform the same matrix multiplication. Suppose we have a n by n square matrix with constant row sum R. Then, in that case, if we perform the matrix multiplication P inverse AP, then we get a block upper triangular form, where the leading coefficient element here, entry here, is the constant row sum of the matrix A. Here, the vector xt is the vector obtained from first row after deleting first element from the first row of A. And the matrix A1 here is the matrix we can obtain from the principal submatrix by deleting the first row and first column minus j n minus 1 into x transpose, where j n minus 1 is the n component vector with all entries are equals to 1. So basically, the A1 matrix is the principal submatrix A one by one minus a matrix whose each rows are equals to X transpose. That is eventually we get a vector we get after deleting first element from the first row. So from this equation here, what we can tell, that all the eigenvalues of the matrix A1 are also eigenvalues of the matrix A. Okay, so we can construct here a matrix of order in -1. So A1 is not only the one matrix, similar way we can actually define several matrices. How? For that, first we take the permutation matrix E2, E3 up to EK, E1, then EK plus 1 up to EN. Then we do the multiplication PK inverse A PK. So what we are doing, we are just interchanging rows and columns of the matrix A. Okay, so first row of A is going to second position, second row position, second is going to third, third is going to fourth, and kth row is coming back to first row, and similarly the columns. Whereas the k plus 1th, k plus 2 up to kth rows are at the same position and corresponding columns also. Now here AK transpose, you can write that AK matrix as AKK, AK transpose Y, and then the principal submatrix obtained by deleting the kth row and kth column. In that case, AK transpose is the vector obtained by deleting kth element from the kth row of A. Now we perform the similar multiplication here. P inverse AK and into P. In that case, the resultant matrix is again a block upper triangular matrix. And in that case, this AK here we can define as the principal submatrix obtained by deleting kth row and kth column minus Jn minus 1 AK transpose, which is equals to a k by k minus a matrix whose each row are equals to that alpha k transpose. That means the vector obtained by deleting kth element from kth row. So where we can apply these observations? So first of all, note that the adjacency matrix of a simple regular graph, in that case, row sum for each row equals to the regularity of the graph. Second case, we can apply this result to the Laplacian matrix of connected graph. The Laplacian matrix is defined to be L equals to D minus A, where D is the diagonal matrix of vertex degrees. The Laplacian matrix has row sum each row sum equals to 0. So we can definitely apply those observations to Laplacian matrix also, and then we can apply the result to the normalized adjacency matrix, where the normalized adjacency matrix of a connected graph is defined to be D inverse into A. Now we recall the famous Perron-Frobenius theorem. Before that, we just define what is irreducible matrix. A square matrix is called reducible if there is a permutation matrix P such that P transpose AP is a block upper triangular matrix. In other words, we call a matrix reducible if we can transform it into a block of a triangular matrix by interchanging rows and corresponding columns. A square matrix is irreducible if it is not reducible. Suppose we have a n by n irreducible matrix which is non-negative. So non-negative means all the entries of the matrix are non-negative. Then the Perron-Frobenius theorem states that the matrix A always has a positive eigenvalue row with positive eigenvector. That means a vector with all entries positive. Not only that, multiplicity of that eigenvalue row is exactly equals to 1, and rho equals to the spectral radius of the matrix. In fact, rho is the only eigenvalue with a positive eigenvector. Now we use the Perron-Frobenius theorem to our observations. Let A be a non-negative irreducible matrix with constant row sum R. Okay, so any square matrix with constant row sum R always has the eigenvalue, then R is always an eigenvalue of A with all one vector as corresponding eigenvector, and all one vector is a positive eigenvector. That means the multiplicity of the eigenvalue R here is exactly 1. Then we use our observation to establish the following theorem. Okay, so for a non-negative irreducible matrix with constant row sum R, we can say that any eigenvalue of A other than R is also an eigenvalue of the matrix AK equals to the AK by K minus Jn minus 1 into AK transpose, where AK transpose is the vector obtained by deleting kth element from kth row of the matrix A. Alright, so we basically use this result as our base result, and later on we obtained our eigenvalue localization theorems or eigenvalue bound for those adjacency matrix and normalized adjacency matrix. Now, basically, we given 3 approaches in our papers, but here we only discuss one. So, for that, first we define the famous Gershgorin disk theorem. So, given A is a n by n complex matrix. For that matrix, the ith Gershgorin disk is defined to be the disk whose center is at aii and with radius equals to sum of modulus of all elements in ith row except the diagonal element. So for a n by n matrix, there is actually n Gershgorin disk. Then the Gershgorian theorem states that for any n by n complex matrix, all the eigenvalues of the matrix lie in the union of all Gershgorin disks. Okay, now we use that theorem and that theorem to establish our results. Okay, so first we take a quick example and we try to see how all this thing works. So suppose we have a given matrix S here. So you can see here the matrix has row sum equals to 1. Every row has sum equals to 1. Also, the matrix is irreducible here. Now, first we try to find out what is S1 for that matrix. So S1, first we take the principal submatrix obtained by deleting first row and first column. So that is exactly that matrix minus we take the first row, delete the first element from first row, and we make a matrix with each row equals to the entries 0.25, 0.3, 0.2. And after subtraction, we get our S1. Similarly, we can find out S2, S3, and S4 also. Our theorem states that, so this is the row sum here for the matrix S here is 1. So from our theorem, we can say that all eigenvalues of S other than 1 are also eigenvalue of the matrix S1, also S2, S3, and also S4. Now we apply the Gershgorin theorem to S1, S2, S3, and S4, and we obtain these four regions here. Now, from the theorem, what we can say? All eigenvalues of S other than 1 lies in the region. Also, all eigenvalues other than 1 lies in that region, and also in that region. So, if we take the intersection of all four regions, after that also we get a region, and that region will contain all eigenvalues of A other than 1. Right? So, using this fact, we actually state the following result. Let A n by n be a matrix with constant row sum R. Then all eigenvalues of A lie in the region intersection I equals to 1 to n GAI union R. So GAI gives you the Gershgorin region for the matrix AI, and we are taking union to R. So we are including the eigenvalue R also. And since all AI union R contains all the eigenvalues of A, so intersection also contains all eigenvalues of A. Where GAI has the form Z belongs to C such that Z minus AKK plus AIK less than equals to that sum. Correct? Now, we now apply this result to obtain eigenvalue bound for different classes of matrices related to graphs. First, we try to apply this result uh, to adjacency matrix of regular graphs. For that, let V be a regular graph with vertex set 1 to n, and A be the adjacency matrix of G. Okay, so first we try to find out the Gershgorin region for A1. So if we calculate A1, that will be the principal submatrix obtained by deleting first row and first column minus the matrix whose each row are equals to the vector obtained by deleting first element from first row of the adjacency matrix. So that is exactly equals to A22 minus A12, A23 minus A13, and so on. Right? Now, to find those, we now find the Gershgorin disk of A1. So for that, first we try to find out what will be the centers of those Gershgorin disks. So centers, possible centers are AJJ minus A1J. Since we are considering the adjacency matrix, so AJJ is always 0. So the diagonal entries of A1 will be minus 1 if the vertex J is connected to 1 by an edge and 0 otherwise. So here we have two possible centers for those Gershgorin disks. One is at minus 1 and another one is at 0. Now other entries of that matrix, we have three possibilities for the other entries of that matrix. So any arbitrary entry, we can write this one as a kj minus a 1j, right? So that will be minus 1 if j is connected to 1 and k is not connected to j. That will be 1 if j is not connected to 1 and k is connected to j, and that will be 0 for all other cases. Now, we consider two cases. First, the the disk is centered at minus 1 and the disk is centered, then the disk is centered at 0. When the disk is centered as minus 1, we get the disk as z mod of z plus 1 less than equals to 2r minus 2n 1 comma j minus 2 if j is connected to 1. Okay, here in 1 comma j denotes the number of common neighbor between the vertex 1 and j. And when j, so this would be j is not connected to 1. Okay, so for the second case, if the disk is centered at 0 and that occurs when j is not connected to 1, in that case we get the disk mod of z less than equals to 2r minus twice n 1 comma j, while n 1 comma j denotes the number of common neighbors between the vertex 1 comma j. Now we have calculated this disk for the matrix A1. Similarly, we can calculate them for A2, A3, and so on up to AK. And after calculation, we get a bound for eigenvalues other than R, eigenvalues other than R. So that is stated as minus 2R plus some maximum over minimum of alpha ik, and then 2R minus maximum minimum over beta ik comma R. Okay, while alpha ik we can define as 1 plus 2 n I comma k if I and k are connected by an edge, and 2 n I k if I is not connected to the vertex I. And similarly, beta ik equals to 3 plus 2 n I k if k is connected to I, and 2 n I k if k is not connected to I. So this one we are getting for the case when the disks are centered at -1, and this one we are getting when the disks are centered at 0. Okay. Next, we try to construct a bound for the normalized adjacency matrix. Before that, we just define what is the normalized adjacency matrix. For normalized adjacency matrix, we take a graph which is finite, simple, connected, and undirected with the vertex set 1 to up to n. Then the normalized adjacency matrix is defined to be the matrix whose entries are, whose ijth entries is defined as 1 by di if I and j are connected, and 0 if I and j are not connected or otherwise. Okay, so if A is the adjacency matrix, then this normalized adjacency matrix is equals to D inverse into the adjacency matrix of the graph. Now we recall some properties of the normalized adjacency matrix. So the normalized adjacency matrix is similar to the matrix D to the power half into adjacency matrix into that matrix A D to the power half, which has entry 1 by square root of D ij if I and j are connected, and 0 otherwise. So that matrix is a symmetric matrix. So that gives all the eigenvalues of the matrix A, normalized adjacency matrix, are real. Summation I equals to 1 to n aij equals to 1. So the matrix A has exactly di number of entries equals to 1 by di in the ith row. So that gives some sum of entries in each row here equals to 1, and that gives 1 is an eigenvalue of A with all 1 vector as corresponding eigenvector, and all other eigenvalues lies in the interval -1 1. So this is because of the Perron-Frobenius theorem. right? So when by the theorem,
Ranjit,
yeah,
is there a typo in point number 1?
is there typo?
D power, is it minus half? First one also?
Yeah, yeah, yeah.
Ah,
It should be minus half.
yes.
Yeah, it is a typo. Yeah. Because we can get the matrix. So the matrix is um, wait a second. No, that's not a typo. That's not a typo. Sorry, that's not a typo. Hmm. Okay, so actually the form of that matrix is equal to d to the power half into adjacency matrix. Sorry, d to the power minus half into adjacency matrix into d to the power minus half. So here, in that case, you have to normalize the adjacency matrix. Hmm. So there is no typo here. Okay. All right. Okay. Okay. So by Perron-Frobenius theorem here. Okay. So Perron-Frobenius theorem states that all eigenvalues of the normalized adjacency matrix has modulus less equals to 1. And since the eigenvalues are real here, so we can say that, and obviously, since we are considering connected graphs, that means the normalized adjacency matrix here is irreducible. So obviously, from Perron-Frobenius theorem, we can say that all eigenvalues of the normalized adjacency matrix other than 1 lies in the interval -1, 1. And -1 is an eigenvalue if and only if the graph is bipartite. All right. Now, note here one thing. Okay, for this matrix here, all the diagonal entries of that normalized adjacency matrix are 0. Right. So that means, and obviously rho sum equals to 1. That means if we apply the Gershgorin theorem here directly to the normalized adjacency matrix, so that will give you the uh, complete unit disk, right? But after performing that, after using that result,
Mm-hmm.
yeah, after using that result, actually we get non-trivial bound for the normalized adjacency matrix, which can state as this one. Okay, so -2 less than equals to maximum I belongs to G, then minimum alpha ik, comma 1 less than equals to lambda less than equals to 2 minus maximum over I belongs to G, minimum I not k not equals to I, beta ik 1. Okay, for alpha not equals to I, we can define that alpha ik and beta ik as follows. So alpha ik here is 1 by dk plus 2 nik by maximum of di comma dk. If k is neighboring to I, and 2 nik by maximum of di comma dk if k is not connected to I. And beta ik equals to 1 by dk plus 1 by di plus 2 nik by maximum di dk if I is neighboring to k is neighboring to I, and 2 nik by maximum of di dk if k is not neighboring to I. Okay, so we get these two different form of constant here. So parameters here alpha ik beta ik, that is because we can have two different type of centers for those matrices ai, right? So one is possibility 0. For 0 we get here beta ik, And for the form 1 by di, in that case, we get that alpha iq. Okay, so I think that's all from me. And there are a lot of result in this direction. You can find this one from that paper, Eigenvalue Bound, for some classes of matrices associated with graph. And this is the base paper. So every the first idea you can get from this paper. Okay, so these are all the references. Yeah, thank you.
Okay, thank you, Ranjit, for the interesting talk. So, if you have any doubt, please ask now. Okay, if there is no doubt, thank Ranjit, and then yeah, thank you, Ranjit.
Yeah,
Okay. Okay, so Ranjit, please send the slides. I will upload in the website.
yeah.
Okay,
And
and as usual, the slides and video will be updated in the website by tonight. Okay.
thank you.
Yes. So next week we will meet. I think hopefully Professor. Mm, just a minute. I just check next week who will speak. Okay, next week Professor Amitav Bhattacharya from Tata Institute. He will speak. Okay. Okay. Thank you.